Good evening, everyone. Hope you can hear me. Okay, I'll start. My name is Sarat Sreepathi. I'm a computer scientist at Oak Ridge National Laboratory. Uh, today, I'm going to talk about performance analytics for computational experiments, PACE. So this work is in collaboration with a number of people who are identified here. So this originally started out in 2018 as a personal project. I have enlisted the support of 2 students over in the initial period to build up a prototype. And Yang Sung Kim has recently joined our team at Oak Ridge and has contributed to some new features. Many of you might be aware of Pat Worley. So he's special thanks to him. He has incorporated a lot of performance best practices and specifically performance archiving capability within the E3SM project, and that has kind of paved the way for this effort to come and play. PACE is a framework to collect and present performance data from E3SM simulations, and I will get into the details of that. Next slide. Okay. So in the off chance that you're hearing about E3SM from me, this is DOE's climate model. So there are about 70 FTEs spread across 8 DOE labs and universities. The primary mission is to look at energy water issues for the next 4 decades or so. The key computational goal is to build a model that can leverage DOE supercomputing resources and utilize them efficiently. So currently that has translated into building a GPU-enabled model to take advantage of these architectures. You can find links for that if needed. And I wanted to give a shout out to my project colleagues who are going to talk later this week. They are going to focus a lot more on the GPU development and various programming models for these exascale architectures. So Luca is going to talk about the next generation atmospheric model. Phil Jones about various programming models, including task-based programming. Isaac is going to talk about a cloud resolving model he's building in C++. And Matt's talking about performance portability using C++. So Min Shu is also in our team, but he is all presenting some work that he's doing with the unified model and the radiation code there. So those talks are coming tomorrow and later during the week. So for PACE, the key goal for this framework is to kind of provide a executive summary of E3SM performance data to interested parties. Those are ranging from different users. So end user looking at a individual performance data, or project leaders trying to collect data about simulation campaigns or analyze overall usage patterns. So some of the kind of capabilities that we're looking at to provide are interactive analysis and deep dives into experiments, and specifically into application subregions, and then drilling down at the lower level. We are also looking at tracking various performance benchmarks and simulation campaigns of interest. So this is a complex model which is run in many different configurations, and we are trying to keep track of all those. What are the characteristics of those various campaigns? And this is also forward-looking in the sense that we are looking into performance research on how do you do optimal resource allocation, how do you load balance these multiple components in a coupled configuration, and what kind of process layouts we use. And finally, we are looking at, as always, performance engineering is focused on identification of bottlenecks and then doing targeted optimization based on those. So what's the kind of performance data that we collect within the model by default? So we have a lightweight performance profiling layer that is turned on by default. So every model run collects this data automatically. So we use general purpose timing library GPTL timers. This is a capability developed by Jim Rosinski and integrated into E3SM. So this is used to mark the start and stop of various application phases. So at the beginning of any important submodule, you can say start application phase name, and then later on you can do a stop timer as well. So, and these can be recursive, so you have higher level timers and then child processes or child phases underneath that. this is also collected across various MPI, multiple MPI ranks, and we can get aggregate statistics for a parallel run. So we are looking at MPI max, MPI min, how much load imbalance is there, and you can collect all those statistics. So they look at collecting computation timers, communication, MPI, even IO performance data. So all of this is collected by default. And we have this practice called performance archiving on all the major supercomputing centers that we run, as well as the dedicated clusters we have for the E3SM project. So we have a location that is shared by all the, throughout the project-wide location, and then every job that is run, every simulation experiment that runs, writes out its provenance data, as well as the timing data from those experiments into this structure. So basically, it collects all the model inputs, as well as the timing output files from these runs. This is not capturing the model outputs like the JNet CDF files or HDF or any other formats that we have. So this is primarily looking at model inputs, XMLs, and then the timing outputs from those. So we have a hierarchical structure with multiple users, different cases, and then the specific job IDs for each of those. And this capability is enabled on all E3SM supported machines. So this includes every DOE supercomputing center, leadership facilities at Argonne, Oak Ridge, and NERSC, as well as some dedicated resources we have for the E3SM project. So let me kind of give you a brief overview of the architecture that we have. So on the left, you have these different centers or supercomputing resources that E3SM project users use. So on a typical machine, you have somebody configuring the model for a couple run. That data is now stored in the project-wide performance archive location. So that data is now uploaded into a PACE architecture, so PACE database. So the way that works is in the middle, you have a set of resources. So these are all being deployed in the Oak Ridge private cloud. Basically, there is an application server, which is the focal point of all these requests. So it receives the data from the simulations run on these individual machines, supercomputers, process the data, parses them, and populates as several database tables for the metadata, and also stores the raw files and other attributes in a file server. So you have this kind of interlinked structure in the middle that is providing the core infrastructure for PACE. And on the right, you have users accessing this data through a web browser. So there is a web portal that is the UI for all this data. They can query their experiments based on various model attributes, machine, user, comp set, which is the problem configuration name we use for our runs, resolution, model resolution. There are a bunch of other attributes you can search as well. So once you pull up a particular experiment data, you can then deep dive into the performance for that particular run. You can also compare across experiments. I will show these in a demo, so that will be more clear, but architecturally, this is how it looks. We have added some, so this, as I said, this started out in 2018 as a prototype, and slowly we have added many features. So some of the recent capabilities we did are processing the model inputs for easy, kind of easy viewing and easy filtering of things. So we are now processing a bunch of XML files, nameless files, which are Fortran input files, and any other file that is out there in the provenance directory, some other logs, logs from each of these components and other things, they're all captured, and we have the raw data from all those experiments. So we have zip files of all those, as well as parsed outputs stored in database tables. As of now, or as of yesterday, late yesterday night, we have about 34,000 experiments in the database, and a bunch of associated corresponding file input files as well. Another capability that we have recently added was, previously we required some manual input into how these data is uploaded from each supporting center. So as a project, we have a point of contact for each platform that we run on, and they're expected to periodically upload this data into our database. But we have done away with that manual intervention, and we have now automated everything this required setting up some service accounts on some of these machines because uh, they have two-factor authentication requirements, and to actually work around those, we had to get some security permissions and deploy this automatic upload capability into that. So this is now enabled on all the E3SM supported machines. So we now, for all practical purposes, we capture every single E3SM experiment that's run on in the DOE landscape on these supercomputers. And on the right, I have a screenshot of how the interface looks like for a arbitrary name list file that you're looking at. So you can pull it up. You can then filter down into particular variables if you're looking at what's the provenance of that particular experiment, and go on. I wanted to present some aggregate statistics. So we have about, so the data within the PACE database now has information from 178 users. So bear in mind, this is unique usernames. So a particular user may have, the unique user might have different accounts on different machines. So it will count 178 usernames, so to speak. And we have data from about 10 platforms. We have some defined benchmarks that we track within the E3SM project on high resolution atmosphere and high resolution ocean. We keep track of these things for every model release, and we are trying to add more smaller benchmarks as well. So this kind of provides a unified interface for us to look at all this data over time. And we also collect data for various simulation campaigns. So some of these names might make sense for project insiders, but high resolution model runs, deck simulations. We also have a kind of a affiliated project within the exascale computing project, which is the DOE's project looking at deploying the exascale machines as well as the corresponding applications. So within that, E3SM is developing a cloud resolving capability using a super parameterization approach. So it contains data from those super parameterization runs as well. There is also cryosphere and biogeochemistry campaigns and data from those. So all in all, about 34,000 experiments in total, and about 900,000 plus model input files and timing files. So the overall database has about 1 million files. Some of these are processed and they are stored in the database, and also you have additionally all the raw data available in the zip files as well. So 1 million plus files and 35,000 odd zip files as well. So some of this data is kind of useful for us to plan for compute allocation proposals. So what kind of simulation campaigns we are planning to run, where are we planning to run, and how do we go after those large DOE allocation proposals. So you need to demonstrate application readiness as well as kind of an estimate of what resources you need. So it's very informative in terms of planning those things out. And within E3SM, we also have plans for dedicated procurements. So we have done in the past, and we are staging up a new machine as we speak. So it is also useful for planning out some simulation campaigns, and if they are better suited for a dedicated cluster environment, it's also useful in planning out those compute procurements as well. So I will just highlight a couple of graph types that we can get through the PACE portal interface. So the first one is what we call a tree graph. Basically, it takes the timing outputs from a individual experiment, and then you can recursively, interactively dive down into the detailed performance data for a particular process. So these kind of timing outputs are written out for every root process of a component. So in a typical run, you have in a couple run, you probably might have about 3 or 5 timing files. So basically, it lets you drill down into that particular configuration, and you can also pull up the MPI level timers. So whether it's the MPI wall clock min or max from other processes as well. So that's one view. that same data can also be visualized as a flame graph that is shown below. It's kind of a compressed view of all the data that you get from the interactivity there, but it's also looking at the same data. So it's kind of a stylistic preference of what you want to look at. But these two graph types are the primary resources that people can get to, can kind of drill down into their experiments performance, and then there are other tools and other revenues to kind of compare with other experiments. So these days, I mean, behind any simple website, there lies a complex technology stack trying to make it all happen. And pace is similar in that manner. Behind the simplicity, there is a whole lot of stack and complexity. So in terms of infrastructure, because of DOE security requirements and others, we are using Oak Ridge private cloud resources for deploying this. We call it CADES, which is Oak Ridge private cloud, and we have an OpenStack virtual machine on top of it. That's the primary server running all these components. And within that, we have various application components. So a primary web server, which acts as a reverse proxy. So this is the one that intercepts all the user requests as well as the data upload requests from the remote supercomputers. And then there is an application server written in Python using Flask. So that's the middleware layer which brings all of this, which has actual processing logic for parsing those experiments, database ingest, as well as retrieval, and then sending the data out to the visualization layer for timings and plotting graphs and other things. And there is a Minio file server. So this is basically object-based storage for storing all the raw data. So all these 30,000 zip files that are there, they're all kind of stored in this, with the metadata being stored in the database. So it's kind of a two-level, two-tier storage, and you can easily retrieve raw data based on a particular experiment. And finally, we have decided to use MariaDB database, which is a fork of MySQL. So this is our second iteration at building a performance database. We have previously tried to utilize MongoDB, the NoSQL databases, and they have their advantages, but certain limitations came into play. And the kind of data that we have for E3SM model simulations, it has a mixture of structured and semi-structured data. So there is a better fit for something like MariaDB, and we were able to get away with some of the advantages from the NoSQL world, where you can mix in some flexible schema as well. And finally, we have a lot of JavaScript-based visualization and front-end based developments for that. So on the right, I have a simple visualization pipeline where you have data being retrieved from the database using Python middleware, and then that's being sent into JavaScript, which can do a DOM traversal or do other kind of graph types based on that. And finally, I mean, cybersecurity compliance. So this is a major pain point over the last year or so. So at a DOE lab, I mean, you have various directives that you need to, DHS guidelines and other things that you need to adhere to actually deploy a public-facing web server. And in this case, we are doing a dynamic service as well. So everything needs to be secured. And we had a dedicated penetration testing team test out our stack, identify some vulnerabilities which we were able to address because they were very diligent at creating malicious packets. So in fact, I mean, they constructed malicious zip files as experiment data. So we are now able to plug all those, and now and basically, so that's the kind of effort that you need to deploy this at a DOE lab. So kind of switching gears here. So what are the kind of performance research that we want to do with this data? So on the left, I have a PE layout diagram in our parlance. So this is kind of the process layout of various components within a coupled model run. So the x-axis is MPI rank, so processor number, and the y-axis shows simulation time. The different boxes that you see represent different components. So atmosphere, ice, ocean, land, and coupler. So those are the most time-consuming components in a coupled run. So these vary from different configurations, but normally atmosphere and ocean are usually the most compute-intensive components. So the intention here is to improve the overall throughput of a simulation by load balancing and optimally allocating the resources to these components. So sometimes, I mean, even if you give additional resources to a particular component code, it may not be able to scale well or utilize those resources in an efficient manner. So this is a balance, and some of this data is useful for us to understand individual component scaling and then map it into how it might perform in a coupled configuration. And all the previous coupled configuration runs. So we do a lot of this tuning process layouts, and this kind of data is useful for that. And on the right, I have it's a comparison of time spent within various atmospheric processes. So this is just time within a atmospheric model run. So the idea here is to look at various configurations. So I think this is showing low-res model versus the high-res model, and then we're trying to compare how different component scale and where we should focus our optimization efforts on. And so continuing that theme, so what we have currently is I like to think of it as an assistant model. So you have your minion helping you out with your simulation planning. So if I want to run a coupled model configuration and run 50 years or I mean, for the high-res model, you're probably looking at 50 or 100-year runs. So what kind of resources should we plan for, and which among our platforms is a better fit? So these are the kind of questions that it can answer based on even existing data. So in a similar manner, process layouts, you can look at the existing data and figure out what's an optimal layout there. We can also do a lot of data analysis and statistical analysis on existing data to figure out if there are areas of concern like underutilized resources or suboptimal kind of layouts. We can also do anomaly detection and even performance variability as well. So with a lot of IO intensive runs, you see a lot of performance variability, and it gives us a way to quantify that variability and also understand where what might seemingly be variability from one aspect, you're mistaking it for something else. So the existing data is useful for all that. And also it helps us at the project leadership level to look at allocation reports and usage. You can drill down into individual users or who are the most active users for allocations and all that. And we are now integrating a lot more detailed IO performance data within this framework. So we will be able to do more read and write bandwidth for every experiment out there. So we have that kind of data for the overall model for some benchmarks, but now it will be an always-on capability analogous to core profiling. And the future, what we want to do is build up so based on all this data, we wanted to understand what are the kind of, when a particular experiment's data is imported, we can even identify where potential optimization opportunities are. So whether they may be in simple process layout, or we might notice that data from an individual component or improved kernel outperforms whatever is in a particular experiment's version. So we can then direct, we probably need to pull this out, or we probably need to apply these kind of optimizations. So they could be at a macro level in terms of resource layouts, or at a micro level, use version 1 or use version A of this kernel rather than version B of that kernel. So it can span the hierarchy of these optimizations. Again, optimal resource allocation. So this is where if we are planning a new simulation campaign, we can, instead of starting from scratch, we can lay out our core requirements, and this wizard can analyze the data from the existing database and then figure out and recommend a particular layout to start with. So those are kind of this is kind of a big ask, because right now this is a performance expert's core job in tuning that layout. So hopefully we will be able to get to a place where it will be more intelligent in that selection. And one topic of interest, I mean, statistical analytics. you can call it machine learning too these days, but there is potential for looking at some of those methods to do communication optimization, fine-grained task mapping at the MPI level. And even looking a little bit into the future. So Frontier and A21 are going to be heterogeneous architectures, but even there, you kind of know which components are more suitable for CPU versus GPU. But in the future, there could be even more heterogeneous resources. So some of that kind of information, it will be useful to do more fine-grained tasking and allocation there. So finally, active monitoring and reporting. It's a good feature to have. Project leadership definitely likes it. So if you don't have to go and pull information yourself and you're getting alerts based on particular criteria, that's always good. So I will stop with the presentation aspect here, but I wanted to show a small demo. So first, I would like to acknowledge support of the E3SM project and DOE Office of Science for the student support, and Oak Ridge Cloud Resources for all the infrastructure here. I have some links in the presentation. So there is the portal link. I have it there along with some documentation pages. And there are also a couple of video tutorials about various portal features and how to upload data here. And the actual portal data is available at pace.ornl.gov. So I wanted to highlight a few of those features of the portal before I end for the day. So this is the homepage view of this performance portal. You can search for experiments from a particular machine or a particular user. So Summit, you can pull up recent experiments. You can sort by various attributes. You can, so here I'm sorting out by the largest process count for experiments here. So we have some high resolution atmosphere benchmarks that are being run. There is also various other attributes. You can sort by run length or the model throughput. And by default, it shows you the experiment date, the most recent experiments up top. You can also look at specific users. So it will autofill. So if you're looking at a particular experiment and a user combination, so you can do that as well. You can, so at the higher level navigation, you have data for the various platforms that we have data for. And we also have benchmarks, as I mentioned, high resolution atmosphere, high resolution ocean. There is also data for other things. So SCAT, one attribute I wanted to show you was once you filter out into a certain category, so you're now looking at a particular model configuration data. This is a overall scatter plot for what's the model throughput based on the various characteristics. So the x-axis is the total MPI ranks, so to speak, and the y-axis is the model throughput simulated years per day. So you can see the range of throughputs that you have. So it's kind of a poor man's performance variability study, so to speak. So you can see the span of the performance of your various experiments in this simulation campaign. And we have data for various, as I said, tech simulations, high-res model simulations, cryosphere, and similar things. So once you select a particular experiment to look at, there is a view called experiment details. It shows you a lot of the metadata, which user, which machine, what date, and what's the case name, which is our naming convention for problem configuration, the version of the model, and a bunch of other timing results. So on the right, you have this model throughput diagram. So this is where you know how these components are laid out MPI rank wise, as well as the performance data from that. And you have the ability to download the raw data. So you get the zip file for this particular experiment, and then you can pull off. There is also handy component throughput table and all the model input files that you can look at. So the tree graph that I mentioned in the presentation, so this is how once somebody, so you can get to a particular experiment and you can look at the tree graphs and flame graphs and a bunch of other things. You can click from there, but the interface, how it pulls up, basically you can look into a particular model, and then you can deep dive into that particular timers and recursively. So this is one view. And as I mentioned, the flame graph is an alternative way of looking at the same data. So you can drill down deeper, or you can look at a higher level. So this is the atmospheric model. You're looking at cam run 3, and then various the dicore, various timers within the dicore. And this is a aggregate statistics across all the MPI ranks. So you are looking at the MPI wall max for these timers across different ranks in a parallel process. So tree graph, flame graph, and these things. This is the name list viewer. You can interrogate a particular model input file and then drill down deeper into it and filter based on that data. This is another comparison view of specifically the atmospheric model timings. I will stop here. Basically, there is a lot of features, and you can look at the more linked videos for more. But to summarize, basically, there is a lot of features here, and I would like to take questions now. So, thank you. So the first one, what is the overhead of performance profiling? So we are using GPTL timers, which are, so we have the overhead information as well in the timing files. It is very low. So these timers are not doing anything fancy. So it's just a simple counter based one. They have the ability to intercept so we have the ability to intercept PAPI events and collect more detailed data, hardware counter kind of data. But in general, the regular timing profiling, it's very low overhead, and it is always on. So at an individual call level, and you're looking at more, these are application time phases. These are not loop level timers. So 10 power minus 6 or lower, it's not going to really add up a lot. So, and we actually compensate for even the tiny overhead when we account for these timings.
So roughly, what is the ballpark of the overhead? Is like 1%, 2%, or something?
It's less than 1%, I would say.
Okay. Good.
Okay. The next question is, have you used the database to identify performance issues? For example, identifying when an OS upgrade hurts application performance. Yes, so we can easily compare. So when we have these benchmarks that we keep track of, we can look at if something in the machine environment changed. So even going to a new compiler, or system has gone down for maintenance and we have a new software stack. So when something is iffy, you can see how it compared to the previous run within the database. And sometimes, these are things where a particular compiler version kind of degraded performance. Sometimes it's mostly the file system. You typically have, oh, this used to be run better. It's kind of a subjective remark from a user, but now you have data that you can go and kind of longitudinally study how that performance degraded on that particular platform. So yeah, environment changes we are able to keep track of, and sometimes even purposefully we kind of look at so when somebody does a pull request to submit a new feature, and we expect performance impact from that, and whether it might be an improvement or a degradation, you probably want to quantify it. So we have the ability to look at the database before and after and kind of make the judgment. Hopefully that answers that question. So another performance question. Any experience where teams have used this to submit an allocation proposal? So I am a co-PI on a couple of insight proposals over the years. So I have definitely used it. I have so some of our colleagues within the project have submitted separate ALCC proposals. I know at least they have estimated some of their simulation needs using data from here. And we also have, so sometimes, I mean, in project developments, we have, in the E3SM project, we have next generation model developments, we are what we call NGDs. Even in allocating some of those, pitching new ideas. I remember a time when there was solicitation for new parameterizations to be included that are into the next generation atmospheric model. And they were planning with a lot of these estimates based on PACE data to figure out kind of what budget they might have for these different parameterizations. So yeah, compute allocations, some project planning, and forward-looking proposals as well. And another question, so have you used your database to address E3SM misconfigurations? Misconfiguration. So one of the typical misconfigurations might be using a bad process layout. So that happens more often with certain configurations where they might not be as savvy in a particular platform, and they kind of pick a layout that might not be suitable. So somebody is moving from a core CPU platform onto a GPU based machine, or even from a plain CPU to something like a Core ORNL kind of partition. So there, I mean, when the performance group gets a request to review performance or optimize something, these are the first few things we look at. So process layouts here one, and then IO. So the main misconfiguration is using a older module of IO when they could potentially use a newer, more optimized version of the IO module. So we have recently deployed something called Scorpio, which is a fork of PIO2 along with some optimizations for the DOE supercomputers. And that's one of the major misconfigurations that have been identified. And let me look at anything else in the chat. No. So thanks everyone for being patient, and hope I'm able to answer your questions. Thank you.